Okay. Let's talk about higher or Laplace transforms of higher derivatives. The Laplace transform of the nth derivative of a function little f is the following. It's s to the n times the Laplace transform of just f, little f, which is big F. Minus s to the n minus 1 times f of 0 minus n to the s to the n minus 2 f prime of 0. And we keep going like that. We have the power of s keeps going down and the number of derivatives keeps going up. So this has s to the n minus 1 and it's no derivatives. This is s to the n minus 2 and it's the first derivative. The next one would be s to the n minus 3 times f double prime of 0. And we keep going until there's no more s's, so the last term doesn't have a power of s on it. And that would be when we get to the n minus 1th derivative of 0. I won't bother justifying this. There is a justification in the book. Here's the statement in the book, and before that they justify it a little bit. But the truth is, it's just repeated application of what we did for the first derivative. So I would like to solve a higher order differential equation now. And I chose one that we already knew how to do, and I worked it out the way we know how to work it out. So this is a second order linear homogeneous differential equation with constant coefficients. These are the ones where we set up the characteristic equation. So r squared minus 5r plus 6 equals 0. We factor that to solve for r. I get r equals 2 and 3. That means my solutions are e to the 2t and e to the 3t, and my general solution is any linear combination of those two functions. I did have initial conditions, so I would want to solve for C1 and C2, and the way I do that is I need y of 0 and y prime of 0. So here I can do y of 0 already, so I put in 0 for t. And then here I have to figure out the derivative of what I wrote. So I did the derivative of this to get this, and then I plugged in 0 there to get this. We would solve this system. C1 plus C2 is 2. 2C1 plus 3C2 is 5. I would solve that. I didn't really show the work for solving that, but you would get C1 and C2 are both 1. So our final answer would just be e to the 2t plus e to the 3t. And that's all stuff that we already knew how to do. Let's do the same example again, completely differently, with Laplace transforms. So the first thing I'm going to do is actually just write the same equation again. And then I'm about to do the Laplace transform of both sides. The Laplace transform of y double prime. I have to look at this formula. S squared times the Laplace transform of y minus, here n is 2, so s to the n minus 1, that's just s, times f of 0. And by the way, y of 0 was 2, so I'm going to write 2s. Minus, and then the next term is already the last term. Because we stop when, like, the last term has no s's on it, and the one I just wrote had s to the 1. The one I'm about to write would have s to the 0. So the one I'm about to write is the last one. I would have s to the 0. I feel a bit silly, but I'll write it anyway. S to the 0 times f prime of 0. Y prime of 0 was 5, so I'll write 5. So this is the Laplace transform of y double prime. So that turned into that. Then I would do minus 5 times the Laplace transform of y prime. The Laplace transform of y prime, that's what we did before. It's s times y minus y of 0. Y of 0 is 2. Plus 6. And then the Laplace transform of little y is just big Y. And the Laplace transform of 0 is just 0. Yeah? Okay, so now this is just algebra. Let me collect all of my y terms. So I've got an s squared y. I have a minus 5sy. Oops, I forgot I factored out the y. And a plus 6y. So I'm going to keep those on the left. I'm going to move everything else on the right. So let's see. I've got a 2s. And then this would give me a plus 5 because I'm moving it over. And this would also give me a plus 10. So let me write plus 15. So capital Y is 2s plus 15 over s squared minus 5s plus 6. So all I need to do is the inverse Laplace transform of this. Again, this is not something that we're going to see on that table. However, we can do partial fractions to it. And this time, let's actually do it and not cheat. And let me point something out here. As we're doing partial fractions, of course, I need to factor this bottom. So I just needed to factor this polynomial, which is the same polynomial that I had to factor when I did this the first way. Somehow, whether you're doing Laplace transforms or not, there's just no way to get around the fact that solving this differential equation involves factoring this polynomial. Anyway, we do it, and I would set this equal to a over s minus 2 plus b over s minus 3. Have I made a mistake? Well, let's see. I'll just keep going. I need to solve for a and b, so I would multiply by s minus 2, s minus 3. So I would get 2s plus 15 equals a times s minus 3, b times s minus 2. And then if I put in 2 for s, I'm going to get 19 equals negative a. Yeah, so something feels very wrong here. What has happened? I think this 15 should be a minus 5. Yeah. I had this minus 5 and this plus 10. So that was a plus 5 total on this side, and then I moved it to that side, and that should be a minus 5. Okay. It's a good feeling because just go through and cross out that 15 and replace it with -5, and I think it hasn't mattered too much yet. It was about to. If I had gone much further, this would be harder to fix. So we're there. Now let me try s equals 2 again. Now that this is actually right, hopefully, I would get -1 on this side, and I get -a on this side. So a equals 1. Yeah, that's what I was expecting. If I do s equals 3, then I get 1 on this side, and I would get b on this side. So a and b are both 1. So y, so we said y was a over s minus 2 plus b over s minus 3, and we decided that a and b were both 1. Now I can do the inverse Laplace transform of that. And again, this is just in the table, but I'll show you. 1 over s minus a, the inverse Laplace transform of that is e to the at. So inverse Laplace of this is e to the 2t. This is e to the 3t. Same answer that we got the first time. So yeah, I don't know. I like to do this just to check that two things that we learned both give us the same answer. Somehow I find that satisfying. But so there you have it.